Empirical formulas. Okay, remember we had two different kinds of formulas? Here's one of them. Suppose that the identities of the elements in a sample of a new compound have been determined and the compound's percent composition is known. These data can be used to find the formula for the compound. First, you must determine the smallest whole number ratio of the moles of the element in the compound. This ratio provides the subscripts in the empirical formula. The empirical formula for a compound is the formula with the smallest whole number mole ratios of the elements. The empirical formula may or may not be the same as the actual molecular formula. Okay, empirical formula may or may not be the same as the actual molecular formula. If the two formulas are different, the molecular formula will always be a simple multiple of the empirical formula. Okay, the empirical formula for hydrogen peroxide is HO. The molecular formula is H2O2. Okay, so this is a multiple, right? This is the molecular formula, and this is the empirical formula. This is a multiple of this. In both formulas, the ratio of oxygen to hydrogen is 1 to 1, right? 1 to, well, 2 to 2, but you can reduce that to 1 to 1. The data used to determine the chemical formula for a compound may be in the form of percent composition, or it may be the actual masses of the elements in a given mass of the compound. If percent composition is given, you can assume that the total mass of the compound is 100 grams and that the percent by mass of each element is equal to the mass of that element in grams. For example, the percent composition of an oxide of sulfur is 40.05% sulfur and 59.95% oxygen. Thus, as you can see in figure 1110, 100 grams of the oxide contains 40.05 grams of sulfur and 59.95 grams of oxygen. Okay. Here's 100 grams of sulfur oxide. The mass of each element can be converted to a number of moles by multiplying the inverse of the molar mass. Here's molar mass, right? They've done an inverse here. Just a minute, sorry. Yeah, right. Okay, recall that the number of moles of S and O are calculated in this way. So there's 40 grams of sulfide, but in one mole there's 32.7. Okay, so we have this much. If this all together is 100 grams, okay, these two together make 100 grams. But what we want to find out is how many moles of sulfur are in this 40.05 grams of sulfur. Well, we know that there's 1 mole in every 32.07 grams of sulfur. Am I saying that right? Anyway, yes. So we can do this multiplication, right? Actually, this turns out to be division. 40.05 divided by 32.07 and it equals 1.249. So that's how many moles, because moles is what we have left up here, right? We can do the same with the oxygen. If you don't know how to do this, you need to go back to the first section of chapter 11 and practice that, okay? The mole ratio of S atoms to sulfur to oxygen is 1.249 to 3.747. As you can see, these values are not whole numbers and cannot be used as subscripts in a chemical formula. Aha, we cannot write S 1.249 O 3.747. We have to come up with whole numbers. So how can you do that? We're going to figure that out. The mole can, as a starting point, recognize that the elements with the smaller number of moles, in this case sulfur, might have the smallest subscript possible, 1. You can make the mole value of sulfur equal to 1 if you divide both the mole values by the value of sulfur. So I want to change this to be a 1, right? So I'm going to divide this by itself. It equals 1. But what I do to the moles of sulfur, I have to do the moles of oxygen. So I'm going to divide this, right? Oxygen divided by the mass of the moles of sulfur, and I end up with 3 moles of oxygen. So the ratio is 1 to 3. The simplest whole number ratio of sulfur atoms to oxygen atoms is 1 to 3. Thus, the empirical formula for the oxide of sulfur is SO3. Often in determining empirical formulas, the calculated mole values are still not whole numbers, as they are in the preceding example. So in other words, if you do this math, you end up with not whole numbers here. Okay. In such cases, all the mole values must be multiplied by the smallest factor that will make them whole numbers. So if this is still not a whole number, you got to keep multiplying until you can get them both to be whole numbers. Okay. Here is an example problem. Again, try the problems. Molecular formula. Would it surprise you to learn that 2 or more substances with distinctly different properties can have the same percent composition and the same empirical formula? How is it possible? Remember that the subscripts in an empirical formula indicate the simplest whole number ratio of moles of the elements in the compound. But the simplest ratio does not always indicate the actual number of moles in the compound. To identify a new compound, a chemist must go one step further and determine the molecular formula, which specifies the actual number of atoms of each element in one molecule or formula unit of the substance. Figure 1111 shows an important use of the gas acetylene. It has the same percent composition and empirical formula, CH, as benzene, which is a liquid, yet chemically and structurally, acetylene and benzene are very different. Okay, so they both have a 1-to-1 ratio of C, carbon, and hydrogen, but I'm guessing that they have different multiples of carbon and hydrogen in one molecule. To determine the molecular formula for a compound, the molar mass of the compound must be determined through experimentation and compared with the mass represented by the empirical formula. For example, the molar mass of acetylene is 26.04 grams per mole, and the mass of the empirical formula CH is 13.2 grams per mole. Oh, okay, so I'm comparing these. This is twice as much as this, so I'm guessing that the molecular formula is going to be C2H2, which is going to double, right, and give us the mass for the molecule. Dividing the actual molar mass, here's this is the actual molar mass, by the mass of the empirical formula, this is the least common multiple, right? Indicates that the molar mass of acetate is 2 times the mass of the empirical formula. Okay? So that's what we just did. The result shows that the molar mass of acetylene is 2 times the mass representative in the empirical formula. Thus, the molecular formula of acetylene must contain twice the number of carbon atoms and twice the number of hydrogen atoms represented by the empirical formula. Similarly, when the experimentally determined molar mass of benzene, which is 78.12 grams per mole, is compared with the mass of the empirical formula, the molar mass of benzene is found to be 6 times the mass. Okay, so what is the molecular formula going to be? C6H6, right? The molar mass of benzene is 6 times the mass represented by the empirical formula. So the molecular formula for benzene must represent 6 times the number of carbon and hydrogen atoms shown in the empirical formula. So you can conclude that molecular formula for acetine is CH2 or C2H2. And the molecular formula for benzene is CH6 or C6H6. A molecular formula can be represented as the chemical formula multiplied by an integer n right here. So this is this whole thing right here with the multiplier is the molecular formula. The part that's inside the parentheses is the empirical formula. It's the smallest part of it. So the empirical formula for acetylene and benzene are the same. The empirical formulas are the same, but the molecular formulas are different. This has a multiplier of 6 and this one of 2. Okay. The integer is the factor, the 6 in the above example, which the subscripts in the empirical formula must be multiplied to obtain the molecular formula. Okay, this is also a molecular formula here. Okay, and some samples for you to look at and more examples there. And some practice problems. Try them. The steps in determining empirical and molecular formulas from percent composition or mass data are outlined below. As in other calculations, the route leads from mass through moles because formulas are based on the relative number of moles of elements in each mole of a compound. So this is a flow chart to help you determine what to do. I think you kind of have to have it in your head, not memorize the flow chart, but have a sense of how they relate to one another so that you can figure out how you're going to set up your calculations. Hope this helps.